Hello everyone. In this lecture, we will discuss lifecycle and performance-based material selection in sustainable and resilient architecture. Materials are often introduced as physical components of buildings, walls, floors, structural members, facade systems, finishes, and details. However, in contemporary architectural practice, materials must also be understood as environmental, technical, social, and ethical decisions. Every material has a story before construction and a consequence after use. It is extracted, processed, transported, assembled, maintained, repaired, and eventually reused, recycled, or discarded. For this reason, material selection is not only about appearance, cost, or availability. It directly affects carbon emissions, energy consumption, natural resource use, indoor comfort, structural safety, durability, and disaster resilience. Today's lecture asks us to evaluate materials through both lifecycle thinking and performance-based design. The lecture is structured around 5 main sections. First, we will examine the concept of sustainable architecture and its fundamental principles. This section provides the theoretical background for understanding why material decisions are central to sustainability. Second, we will discuss materials in the context of sustainability, focusing on environmental performance, resource consumption, and long-term durability. Third, we will consider the life cycle approach and environmental performance. This perspective allows us to evaluate materials before, during, and after their use in buildings. Fourth, we will discuss performance and durability criteria in material selection, especially in relation to disaster resilience. Finally, we will examine the impact of material decisions on sustainable architectural design through the example of wood. Wood is a useful case study because it is renewable, carbon storing, structurally efficient, visually expressive, and technically complex. Throughout the lecture, the main idea is that no material is automatically sustainable. Sustainability depends on context, sourcing, design, detailing, and maintenance. By the end of this course, students should be able to define sustainable architecture in a multidimensional way. This means understanding sustainability not only as energy efficiency or green appearance, but as an integrated design framework involving environmental, economic, and social dimensions. Students should also be able to explain the impact of material selection on environmental performance. A building's environmental footprint is not determined only by operational energy use, it is also shaped by the energy and emissions embedded in its materials. Another objective is to evaluate a building material within a life cycle framework. This requires asking where the material comes from, how it is produced, how long it lasts, how it behaves during use, and what happens at the end of its service life. Finally, students should understand the relationship between sustainability and disaster resilience. Material selection should be evaluated as a performance-based design decision that affects safety, durability, environmental responsibility, and architectural quality. Sustainable architecture includes all activities aimed at creating structures that prioritize renewable energy sources, environmental responsibility, and efficient use of energy, water, materials, and space. It also considers future generations throughout the entire life cycle of a building. In simple terms, sustainable architecture is the art of meeting human spatial needs without endangering natural systems. Within this framework, building materials are among the most important factors determining the environmental footprint of a structure. The production of materials consumes energy, requires raw resources, generates emissions, and affects ecosystems. Extraction processes may disturb landscapes, manufacturing may produce greenhouse gases, and transportation may increase carbon emissions. Therefore, the sustainability of a material should be evaluated through production energy, natural resource use, carbon emissions, service life, maintenance needs, and recycling potential. This means that material selection cannot be based only on aesthetics or initial cost. Sustainable architecture requires architects to look beyond the immediate design moment and consider long-term impacts. Sustainable architecture is a holistic design approach that addresses environmental, economic, and social sustainability simultaneously. This approach is based on three fundamental principles: resource management, life cycle design, and design for people. Resource management aims to use energy, water, materials, and space efficiently. In terms of materials, this means reducing unnecessary consumption, selecting low-impact alternatives, minimizing waste, and considering local or renewable resources where appropriate. Life cycle design means that a material should not be evaluated only during the usage phase of a building. Its pre-construction, construction, use, maintenance, and post-use phases should also be considered. This makes durability, reusability, recyclability, and maintenance needs central to material selection. Design for people focuses on user health, comfort, and quality of life. Materials affect indoor air quality, thermal comfort, acoustic performance, tactile experience, and psychological perception. When these three principles are considered together, building materials become a key component of sustainable architecture. Earthquakes, floods, landslides, hurricanes, and forest fires are natural events that may occur with high probability in many regions. These events cannot always be prevented. However, they become disasters when the built environment is not prepared and when necessary precautions are not taken. For this reason, contemporary architecture and urban planning no longer focus only on post-disaster response. They increasingly emphasize pre-disaster risk reduction, preparedness, and resilience. Disaster-resilient cities are physical, social, economic, and environmental systems that can prepare for hazards, recover quickly after damage, and maintain essential functions. The building production process is one of the most critical components of this resilience. Buildings must not only reduce environmental impact, they must also protect life, maintain structural integrity, and support recovery after hazardous events. Material selection plays a central role in this process. A building that is environmentally efficient but unsafe during a disaster cannot be considered truly sustainable. Material selection in terms of disaster resistance does not only mean choosing materials with high compressive or tensile strength. Strength is important, but it is not sufficient by itself. Especially when dynamic loads, such as earthquakes, are effective, several additional criteria must be evaluated together. One of these criteria is ductility. Ductility refers to the capacity of a material or system to change shape before breaking. This helps prevent sudden collapse. Another important criterion is energy absorption capacity. Under dynamic loads, materials and structural systems should absorb energy and delay failure. Continuity and integrity are also essential. Even if individual elements are strong, weak connections or interrupted load paths can cause serious damage. Sustainability should also be included in disaster-resilient material selection. Long service life, ease of maintenance, adaptation to environmental conditions, and reduced environmental impact must be considered together. This holistic approach connects building scale with urban resilience. Wood is an organic material with a fibrous, heterogeneous, and anisotropic structure, produced by trees. It is one of the earliest materials used by humans and has been used for centuries because it is accessible, workable, and naturally available. In sustainable architecture, wood holds a special position because it is a renewable natural resource when obtained through responsible forest management. One of the key environmental advantages of wood is its relationship with carbon. During growth, trees absorb carbon dioxide from the atmosphere and store carbon in their cellular structure. When wood is used in buildings, this stored carbon can remain within the material for a long period. Compared with concrete and steel, wood generally requires lower production energy and can generate lower carbon emissions. However, wood should not be automatically described as sustainable in every context. Its sustainability depends on responsible forestry, controlled harvesting, transportation, processing, protection, and long-term use. The sustainability value of wood also comes from its capacity to combine environmental, structural, and architectural qualities. It is lightweight in comparison with many other structural materials, yet it can provide significant strength when used correctly. This favorable strength-to-weight ratio may reduce transportation energy, and can also be beneficial in seismic regions, because lighter buildings generally experience lower seismic forces. Wood is also relatively easy to process. It can be cut, joined, shaped, prefabricated, and assembled with lower energy inputs than many industrial materials. Modern engineered wood products expand the possibilities of timber architecture by improving dimensional stability, structural performance, and predictability. From a spatial perspective, wood contributes warmth, texture, and natural variation to architectural environments. However, these benefits depend on correct design decisions. Poor detailing can lead to moisture damage, decay, deformation, or reduced durability. Therefore, wood should be evaluated as a performance-based architectural material. To understand wood as a building material, it is necessary to examine its structure. Wood has physical characteristics that can be observed with the naked eye or with magnification. These include color, smell, taste, luster, and fiber structure. At the same time, wood has a complex internal organization that affects its mechanical and physical behavior. There are 3 different cross-sections in the tree trunk: transverse, radial, and tangential. The transverse cross-section is obtained by cutting perpendicular to the tree trunk axis. The radial cross-section is obtained by cutting parallel to the tree's rays. The tangential cross-section is obtained by cutting parallel to the tree trunk axis and perpendicular to the rays, tangent to the annual rings. Wood is fibrous, heterogeneous, and anisotropic. This means that it does not behave the same in every direction. For architects, this is important because wood structure influences strength, shrinkage, swelling, appearance, workability, and durability. One of the most fundamental factors determining the application areas of wood is its physical properties. Characteristics such as color, luster, smell, taste, and texture directly affect both performance and suitability for different architectural uses. Color can vary widely, from very light tones to dark brown or almost black, depending on species, age, heartwood, sapwood, and environmental exposure. Heartwood is usually darker, while sapwood is generally lighter. Luster refers to the way light reflects from the surface of wood. Some woods have a natural luster, and different cut surfaces may show different brightness because of anatomical, chemical, and physical properties. Odor generally originates from extractive substances within the wood. These substances are volatile and may lose their scent over time. Some extractive substances are found in heartwood and can provide resistance against many wood-decaying fungi. Therefore, physical properties are not only sensory features. They may also indicate durability and suitability for particular uses. Taste, texture, and fiber structure are also included among the physical properties of wood. Taste originates from extractive substances and is more pronounced in fresh material and green wood. However, it is generally not an important diagnostic feature in architectural practice. Texture is much more significant. The texture of wood is classified as fine, medium, or coarse depending on cell size and pore structure. Large diameter cells indicate a coarse texture, while small diameter cells indicate a fine texture. Fast-growing trees generally have a coarser texture, while slow-growing trees tend to have a finer texture. Texture affects appearance, workability, finishing quality, and sometimes durability. Fiber structure is another critical property. Regular fiber orientation is important for strength, ease of processing, and reduction of waste. Irregular fiber orientation may reduce strength, cause uneven work, and make processing more difficult. In design, these properties influence whether wood is suitable for structural members, interiors, flooring, furniture, or decorative applications. The processing of wood material results in the formation of annual rings and cells that are cut in different ways. These cuts create various appearance features such as uniform, pyramidal, striped, mirrored, speckled, wavy, flamed, bold, raised, and bird's-eye patterns. The visible shapes on wood surfaces can also be understood through external appearance. Heartwood, sapwood, springwood, summerwood, heart rays, and resin canals all contribute to different visual effects depending on the cross-section. Appearance features are important in architecture because wood is often used not only as a structural material but also as an expressive surface material. In interiors, facades, furniture, and ceiling systems, wood creates warmth, texture, rhythm, and natural variation. However, appearance should not be separated from performance. Some visual characteristics may indicate grain direction, knots, density variations, or other features that affect strength and workability. Therefore, architects should read wood surfaces both aesthetically and technically. The mechanical properties of wood refer to its resistance behavior against deformation and fracture when subjected to external forces. Due to its fibrous and anisotropic structure, wood exhibits different mechanical responses depending on the type of loading and the direction of the grain. This makes wood different from more homogeneous materials, such as steel or concrete. There are several types of loading. Static loading refers to slow and continuously increasing loads. Dynamic loading refers to sudden and shock-like loads, which are especially important in earthquakes, impacts, and vibration conditions. Fatigue loading describes long-term and repetitive loads. Variable loading occurs when the load direction constantly changes. Understanding these loading types is essential for safe timber design. Wood generally performs best when loads act parallel to the fibers. Therefore, structural design must carefully consider load direction, member orientation, and connection details. Elastic properties describe the ability of wood to return to its original shape when external forces are removed, as long as the elastic limit is not exceeded. The modulus of elasticity is one of the key indicators of stiffness. It generally increases as density increases and decreases as humidity and temperature increase. Wood reaches its highest modulus of elasticity in the direction parallel to the fibers. As the angle between fiber direction and load direction increases, elastic performance decreases. The elastic behavior of wood increases its energy dissipation capacity under dynamic effects such as earthquakes. Resistance properties refer to the behavior of wood when the elastic limit is exceeded. Compressive strength is high parallel to the fibers and much lower perpendicular to them. Tensile strength provides the highest strength value of wood when applied parallel to the fibers. Bending strength combines compression, tension, and shear effects. Shear and splitting resistance are especially important for joints, nails, screws, and structural detailing. Dynamic resistance covers the behavior of wood when it is subjected to sudden and shock-like loads. Dynamic bending resistance is particularly important for wooden elements used in bridges, stairs, floors, and load-bearing systems. Several factors influence dynamic performance, including density, fiber direction, annual ring structure, moisture content, knots, and defects. Hardness and wear resistance are also important mechanical properties. Hardness refers to the ability of the wood surface to resist penetration by hard objects. Wear resistance is crucial in high-traffic areas such as floor coverings and stairs. These properties are affected by density, moisture content, grain direction, and surface protective coatings. Safety stresses are another important concept. Laboratory resistance values cannot be directly applied to real structural conditions. Natural defects, environmental effects, humidity changes, and long-term use must be considered. Therefore, safety factors are applied to determine allowable stress values and ensure safe use. Wood is widely used as a building material and, in some regions, as the primary construction material. Its architectural value comes from a unique combination of properties. It is easy to process, supports a sustainable life cycle, has good physical and mechanical qualities, provides aesthetic richness, creates healthy interior environments, and offers a favorable strength-to-weight ratio. In architecture, wood can be used in structural frames, beams, columns, floors, roofs, facades, wall panels, interior finishes, stairs, furniture, and landscape elements. It can also be used in engineered forms such as laminated timber and cross-laminated systems. These products allow larger spans, improved dimensional stability, prefabrication, and more predictable structural performance. Wood also contributes to spatial experience. Its texture, color, smell, and natural variation can make architectural spaces feel warmer and more human-centered. Nevertheless, natural wood requires careful detailing, moisture control, ventilation, appropriate surface treatment, and maintenance planning. Although wood has been an important building material for many years, its use has been limited in some contexts because of flammability and combustibility. Wood and wood-based materials contain carbon and hydrogen, which means they are combustible. Historically, this has led to the perception that wood is disadvantageous in terms of fire safety. However, fire behavior cannot be explained solely by combustibility. Fire performance is a multidimensional issue. It includes ignition time, burning rate, heat spread, smoke development, retention of load-bearing capacity, and the ability to maintain structural integrity during fire. In recent years, numerous methods have been developed to improve the fire resistance of wood in terms of both reaction to fire and structural performance. These methods include surface coatings, impregnation processes, fire retardant paint and varnish systems, structural modification, and the development of engineered wood elements. Therefore, wood fire safety depends on design, detailing, treatment, and calculation. Contrary to common assumptions, laminated wood can show strong fire resistance when properly designed. Solid and laminated timber elements form a control char layer on the surface during fire. This layer protects the inner sections from heat and slows down the burning process. As a result, the load-bearing core can remain intact for a longer period of time. Today, wooden structures can be designed to withstand fire for 30 to 90 minutes, depending on design requirements, element size, detailing, and fire protection strategies. Wood does not suddenly soften, flow, or undergo rapid dimensional change due to heat. By contrast, exposed steel structures may lose a significant portion of their load-bearing capacity within a short period during a normal fire, if they are not adequately protected. This comparison shows that fire performance must be evaluated scientifically rather than through assumptions. Wood is combustible, but its behavior can be predictable when properly designed. When wood's fire performance is evaluated together with proper cross-section sizing, appropriate detailing solutions, and fire retardant applications, it can become a safe and predictable alternative in contemporary building construction. This does not mean that wood is risk-free. Rather, it means that fire risk can be managed through design knowledge, engineering calculations, and material treatment. In sustainable and resilient architecture, the aim is not to idealize any single material. Every material has strengths, limitations, and required conditions for safe use. Wood demonstrates this clearly. It offers environmental advantages because it is renewable and can store carbon. It offers structural advantages because it is lightweight and strong when used in the right direction. It offers architectural advantages because it provides warmth, texture, and natural character. Therefore, wood should be considered a rational building material not only from an aesthetic and sustainability perspective, but also from a fire engineering and performance-based design perspective.